All right, guys, welcome to the second part of the review. This is all about reading a problem and determining whether or not you should use a specific distribution or not. So, let's ask the following question. Find the probability that the third tail occurs on the fifth flip of a fair coin. Now, the difficulty with this is that no x's are defined, no distribution is defined, and so we've got to look at the characteristics. So let's see. So first off, characteristics. Well, this is a weighting question. But we're waiting for it to occur on an exact time, i.e. fifth. So amongst all of the distributions, we want a weighting distribution, but we're waiting for it to occur at the fifth. Now, we're also waiting for the third occurrence. So there's a specific fixed occurrence number. All of a sudden, this is starting to sound very much like the negative binomial. Why? We're going to use an x equals 5. That's on could happen on the 5th, could happen on the 6th, could happen on the 7th. We're going to use an r equal to 3. And because the negative binomial is a repeated Bernoulli, that's what we're seeing up here, we're going to make use of the negative binomial. So that function is f of x equals x minus 1, r minus 1. We're waiting for the rth occurrence. And now we're going to sit in x equals 5 and sub in r equals 3. And so we're going to get f 5 equals 4. Choose 2 over 1/2 to the third times 1/2 to the 5 minus 3 second. And there's our answer. 4 choose 2, 1/2 to the fifth. All right. Next problem. We have a scanning machine. It sometimes misses information. Well, what type of information would like the scanning machine to be? Well, let's be a TSA agent, and we're going to be scanning for metal. So how often are we going to have it miss? Well, let's have it miss 1 out of 100 times is the percentage of missing when you have scanned a metal-containing person. It can't miss when someone doesn't have metal. So, TSA has seen lots of people go by. The people that have no metal are not misses, or we're not talking about any false positive. It's only the people that go by that have metal that we might have a chance to miss. So let's ask the following question. Find the probability that the first miss occurs amongst the first 50 metal-containing people. So, what kind of characteristic does this have? Well, sometimes when you look at a problem, you go, it's hard to spot what the characteristic is. So I'm going to just write a few of the characteristics here, but then I'm going to say, if I have trouble spotting the characteristics, maybe there's a different way to look at it. I'll finish the characteristics here, but I'm going to demonstrate that there's other techniques other than just looking for characteristics. But first off, the characteristic, it appears that this 1 out of 100 is the probability of missing. So if every individual has the same probability of missing, and because I missed one person containing metal, or didn't miss the next person, one can assume that it looks like we have an independence of trials with a p equal to 100 probability of missing, and a success, q equals 99 100ths of finding the metal carrying person. It looks like repeated independent Bernoulli trials. But we're looking for the first miss. That problem that we did before, we were waiting for the third. So somehow the first thing occurring seems different than the third occurring. But the other thing is, it says amongst the first 50 metal-containing people. In other words, we're going to have many metal-containing people go by, and the question is, did we miss? Did we miss? Did we miss? When we say amongst the first 50, it seems like we're waiting for the first one, but we're being asked many probabilities. So, is this a negative binomial? Is this a geometric? Is this something else? Well, let's look at a picture. So here I'm going to do a picture. I'm going to draw a picture of the people containing metal walking by. We either miss or we successfully get them. Now the next one comes by. We either miss or we successfully identify them, and we repeat. Now, the probability that you catch the first one on the first instance is right off the probability that the first miss equals the first scan with metal is simply P. The probability of the first miss equals the second scanned person with metal. Well, it's this, PQ. So each one of these points down there we're interested in. This is a geometric problem, and we need to add up lots of probabilities. Namely, we're going to bring this all the way down to 50 of these, and we want to say, what is the sum of all 50 of those probabilities? We want the sum of, what is this? It's always P, Q to an I. This one is no Q. This one is 1 Q, 2 Qs, all the way up to 49 Qs, and a P. So we want the sum of all of these probabilities. So we're doing the geometric series many times. However, it might be easier to do the complement problem. Let's add up an infinite series. So here's the complement problem. What is the sum from I equals 50 to infinity of P, Q to the I? That's the rest of them. We went the first up to 49, and we're going to take off here. When you write this out, P, Q to the 50 plus P, Q to the 51 plus P, Q to the 52, etc. This is pretty simply factor out the common P, Q to the 50, and observe what's left is 1 plus Q squared forever. This is the geometric series. P, Q to the 50. Sum of the geometric series is 1 over 1 minus Q. And now the complement of this is that one, so we really want 1 minus p q to the 50th over 1 minus q. By the way, 1 minus q is p. We have 1 minus q to the 50th, and q is 99/100ths. This is kind of a neat way to do it. The picture, more than anything, allowed me to see that this is a geometric that's been asked many, many, many times. All right, let's do one more. See if we can spot this one. Shake 3 dice. Find the probability that the sum is less than or equal to 7. Now, in some sense, this is a trick question. Don't mean to mean that it's a trick question. I've just been going through several well-named probabilities. Turns out this is not a well-named probability, because this sum is based upon individual trials. So we're having a shake of a die, shake of a die, shake of a die, 3 independent trials, but we want to look at their sum total. We want to look at each one. And so a previous shake can affect the next shake as if you're going to be successful to get a sum of 7. For example, you shake a 6, you can't win with 3 dice. There's not a 0. So it affects the outcome, the first shake. This is not a repeated independent Bernoulli. Instead, this is one of these questions where you just got to think it out directly. So, the answer to this one is the characteristics is a non-independent trial. Well, let's just write out what this means. How about the probability? The sum. What's the least sum? Well, that would be 3 dice. Plus the probability, the sum equals 4, plus all the way up to the probability that the sum equals 7. Now, some of these shouldn't be too hard. What is the only way to shake a sum of 3? It's a 1, 1, 1. So that would be a 1/6 times 1/6 times 1/6. Well, how can you shake a 1, 1, 2? That's the only way to get 4. Well, here's an instance where I don't know which die shook the 2. So I'm going to think of there being a red die, a blue die, and a green die. And if I write it R, B, G, then there are 3 ways that this can happen. A 1, 1, 2, or a 1, 2, 1, or a 2, 1, 1. Now, even if you didn't have a red, blue, and green die, you can think and imagine in your head that every die is somehow secretly red, blue, and green by some radioactive element or whatever, that even though they look identical, one of these 3 happens. Now, that means there are 3 ways for this to occur, but this is a 1/6 times 1/6 times 1/6, so the probability the sum equals 4 is 3 times 1/6 cubed. Well, let's continue then. Let's look at the probability the sum equals 5. Well, how many ways can you get 5? Well, a 1, 1, and a 3. 1, 3, 1, 3, 1, 1. How about a 1, 2, 2, 2, 1, 2, 2, 2, 1? I don't think there's any other way for this to happen, but each of these shakes is a 1/6, but there's 6 ways it can happen, so 6 times 1/6 cubed. How about the sum equals 6? Now, is this getting harder? And the answer is yeah, it's getting harder. Many more can be written out. So I'm going to write out some of these. 1, 1, 4, 1, 4, 1, 4, 1, 1. How about 1, 2, 3? Oh dear, now that seems to be a lot more. That's a 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, 3, 2, 1. Wow, there's 6 ways just to do that shake. Now, is it possible to have anything other than 2 1s and a 4? If we don't have a 1, there is a 2, 2, 2. And that's one way to happen. So let's count this. 2, 3, 4, 5, 6, 7, 8, 9, 10. Looks like this is 10 times 1/6 cubed. That's, well, what can we say? A bigger count. Now, what about the last one? Well, again, you have to list it out.